In this session, we're going to solve example problems related to free radical halogenation reactions. This includes halogenation at the allylic position of alkenes and also halogenation of alkane molecules. We're going to do a couple of examples to illustrate each of these different situations. And this video assumes that you have already gone through and familiarized yourself with the videos that introduced free radical halogenation of alkanes, as well as free radical halogenation at the allylic position. So let's go ahead and get started here. So our first question is to provide a mechanism to illustrate how the major organic monohalogenation product or products form from the following reaction. So remember that when we say the term mechanism, if you're asked about that in a question, what that's referring to is it's asking you to step by step go through and show each electron transfer that has to take place in going from the starting material all the way to the final product. So we're making a map essentially to accurately show what's happening during the course of the reaction. Mechanisms are useful because they allow us to walk through and predict what products form, and they help us justify the observations that we make about reactions. For example, they help us justify why we observe the certain regioselectivity that we do. Remember that regioselectivity is referring to the preference for making certain constitutional isomers over other possible constitutional isomers. So we're going to try to go through a step-by-step mechanism to predict the major organic products of this reaction and to show how those form. So let's go ahead and do that. And one really good idea, as usual, when we're doing example problems would be to hit the pause button right now and try to go through this reaction mechanism on your own to see how far you get, and then hit play to determine how well you did. All right, so first step of any free radical halogenation reaction, be it an allylic reaction where you're dealing with an alkene or an alkane reaction, is going to be the initiation step. And the initiation step is a step that only has to take place one time in the entire container of millions and millions of chlorines and millions of alkenes or alkanes. And in this initiation step, what's going to happen is that the weak bond that connects the two chlorine atoms is going to break homolytically, meaning that one of the electrons from the covalent bond goes to one of the chlorine atoms, the other electron from the covalent bond goes to the other chlorine. So both of the chlorines get the same number of electrons during the bond breakage. That's why we call it a homolytic bond breakage, because homo means same. So we take one electron from the covalent bond and move it over to the chlorine on the right, one electron from the covalent bond and move it over to the chlorine on the left. And we're using those single arrowheads to indicate the movement of one electron in our map here. So we'll go ahead and draw our reaction arrow here to indicate the product that results from this. And this is going to result in the formation of chlorine radicals. So I'll go ahead and fill in my 3 sets of lone pair electrons. And then additionally, we're going to have an unpaired electron on that chlorine. And that arose from the red electron pushing arrow that we show here coming over to the right, and the other electron from that covalent bond coming over to the left. So that will end up giving us not just 1, but 2 chlorine radicals to go onward. Once those chlorine radicals form in this so-called initiation step, the reaction is totally off to the races. This initiation step only has to happen one time in the entire container in theory. Then what happens is we go into a phase of the reaction referred to as propagation. The propagation steps are referred to as propagation steps because they are self-sustaining, so they can just repeat through and cycle through the propagation steps over and over again, because what we're going to see is that some of the products of the propagation steps can re-enter the mechanism. So we'll look at that as we go through the mechanism here to illustrate how these are defined as propagation steps. And what you're going to notice about propagation steps is that propagation steps will yield radicals. So they're going to yield at least one radical as a product of the step. So let's take a look at the propagation step that's going to go on here. So we have our chlorine radical that formed as a result of the first step of the mechanism. That chlorine radical is really supercharged, very eager to react because it's pretty unstable due to the fact that it has that unpaired radical electron. And that unpaired radical electron is eager to come in and find a way to achieve its complete octet, to attain stability. And so what it's going to see when it looks around the reaction flask for what's available is the alkene molecule. So I'm just drawing the alkene molecule that we started off with up there at the top. And the chlorine radical is going to come over and it's going to be looking for a carbon-hydrogen bond to break because the carbon-hydrogen bonds are weaker than the carbon-carbon bonds here. So it's coming over looking for a carbon-hydrogen bond to break, and it wants to break the carbon-hydrogen bond that will lead to the most stable intermediate. So the question we have to ask here is, what carbon-hydrogen bond can we break that will lead to the most stable intermediate product of this reaction? The most stable location to remove a hydrogen is going to be at the allylic position. That's going to yield the most stable intermediate product. So our allylic positions in this particular molecule are going to be here at the carbon that I'm starring in green and at this carbon that I'm also starring in green. Both of those are allylic positions because they are carbon atoms that are separated by a single bond from an alkene group. And in the case of the allylic position on the right, this one is separated by a single bond from two different alkene groups. And this is going to turn out to be where we should remove the hydrogen, because when we make a radical at that allylic position on the right, indicated with a star, that is going to give us a radical that can be stabilized by resonance from both of those two alkene groups. And by stabilizing using both of the alkene groups, we create extra resonance structures that will allow us to spread that radical electron and share it over additional extra carbon atoms relative to if we were to create our radical over here on the left-hand side. So let's go ahead and do that. So the more positions that this hydrogen is allylic to, the better. And on the hydrogen that we've shown here, this particular hydrogen is allylic to two different alkene groups. And so that's going to allow us to make a particularly resonance stabilized radical intermediate by removing the hydrogen here. So the way that we do that is we will go ahead and we will show our chlorine using the unpaired electron, the free radical electron from it comes over, and that's going to team up with the hydrogen and one electron from that covalent bond. So we show those two coming together, the chlorine with one unpaired electron and the hydrogen with an unpaired electron from the covalent bond there, the CH bond. The other electron from that CH bond is going to go on to the carbon atom there at the allylic position. So I'm showing that electron pushing arrow indicating that one of those electrons from the covalent bond is landing on that carbon atom right there, the allylic carbon. We'll go ahead and draw out the intermediate that would result from this, the carbon radical intermediate, or the allylic carbon radical intermediate, as you might call it. So we'll go ahead and get that all drawn out here. So we'll go ahead and draw in. So we still have one hydrogen left there because we originally had a CH2 group at this position. Now we just have a CH group, and we will have an unpaired electron there because we broke the carbon-hydrogen bond to remove the hydrogen at that position, and we took one of the electrons from that covalent bond and put it on the carbon there at the allylic position. Additionally, from this step, we would generate HCl because we took that chlorine radical and teamed it up with a hydrogen from our alkene there, one of those allylic hydrogens. So this intermediate that we've drawn here can be stabilized by resonance, and so we need to show the additional resonance structures that we have to deal with here. So we're going to go ahead and draw out our resonance structures. I'll actually draw those off to the right here just in the interest of space. So we're going to draw out our resonance structures. Remember that the resonance arrow is this special double-headed arrow. That is important to use that type of arrow because that's what represents resonance, not any other type of arrow. So to do the resonance structures for this, what we need to do is, first off, we're going to go ahead and we can show one of the resonance structures by taking the alkene group electrons on the left, that is the pi bond electrons, take one of those and bring it over one spot to team up with the unpaired radical electron there to make a carbon-carbon double bond where those two arrowheads are coming together. That's showing that we're moving two electrons over to make an alkene group there. We also have, right here in this alkene group, an additional electron, since the pi bond is made of two electrons, and that electron is going to come onto the carbon atom there that it's bonded to. So I'm showing that in green. So we will go ahead and show the intermediate second resonance structure right here. So we're drawing out the second resonance structure. I'm going to draw the carbon skeleton exactly the same as it was to start with, except for where the electrons are going to be located. Because remember that by resonance, the definition is that we are only moving electrons. We are never moving atoms. So in moving those electrons, we're taking the pi bond and we are moving the pi bond over. So the pi bond is going to come to right here using the red electron pushing arrows. And then our unpaired electron is going to end up right here in doing this particular resonance structure. So we'll go ahead and do that. And so now our unpaired electron is right there. We can also do an additional resonance structure showing that we can take the original resonance structure that we started with and we can do resonance using the alkene group that is to its right. So what I'm going to do to show this resonance structure, so I'm going to come in and I'm going to go ahead and go back and show how we can form that third resonance structure. So we go back and start with our original resonance form, and I'm going to show my electron pushing arrows to show how we get to another resonance structure that's distinct from the two that we've already drawn. Okay, so we're going to take our unpaired electron, we move that over to the right with a single-headed arrow. We take our pi bond and take one of the two electrons from that and move it over to put our double bond in there between carbons 2 and 3 in the chain. Then that leaves us with what I'm going to color code in green here. Our second electron from the pi bond needs somewhere to go. It's going to go onto that carbon that's adjacent to it, like so. And we're going to draw out the molecule that will result from those electron pushing arrows. So this is going to be an additional resonance structure. Drawing on the skeleton of the molecule exactly the same. I'm just moving around where the pi bonds are and the unpaired electron. So move the pi bond, go ahead and plug in our electron where our map has shown that it goes, those electron pushing arrows in other words, and that's going to create for us an additional resonance structure. All the resonance structures that you draw for an allylic radical should all continuously show that the radical will always be in the allylic position. That's the case for these three structures that we've shown here. The reason we ended up with 3 was because of the fact that our original molecule, when we looked at the allylic position right here, that was allylic to 2 different alkene groups, highlighted in blue, and so therefore that introduced some additional opportunities for resonance. So now what we're going to do to continue onward, we've done our initiation step where we created chlorine radical. We did our first step of propagation, where we broke the carbon-hydrogen bond at the position of our alkene that would yield the most stable intermediate. The reason that the intermediate we've created here is most stable, boxed off in blue, is because it is the one that has the most resonance structures. It has more resonance than if we were to remove a hydrogen at a position that was allylic to only 1 group. We have it allylic to 2 groups here. So we'll take those 3 intermediates. Each of those 3 resonance structures is going to go into the next step, which we could also describe as propagation, a step that's going to give at least 1 radical product out of it. So we'll go ahead and redraw those here in step 3 of the reaction mechanism, which we describe as propagation as well. So in this propagation step 3, what we're going to do is take each of those 3 resonance structures, and they are going to react with another unit of Cl2 from the container. And it's reasonable for those to react with another unit of Cl2 from the container because of the fact that we're assuming there's millions and millions of alkenes and millions of chlorines in this full container at the beginning of the reaction at least. So we'll go ahead and draw out our 3 molecules, our 3 resonance structures. So I'm just drawing what we had created there as a result of step 2 of the mechanism. So there's one of our 3 resonance structures. Just double checking to make sure that I've drawn it right, which I haven't quite drawn it right here. Always a good idea to double check and count your number of carbon atoms a couple of times to make sure that you're on track with this. So now I think I'm good to go. Not quite. So make sure that you're counting how many carbons are in your chain. Going along here, we have 1, 2, 3, 4, 5, 6, 7, 8. So I should have 8 in the structure that I'm drawing here. 1, 2, 3, 4, 5, 6, 7, 8. And make sure we're getting our carbon-carbon double bond in the right place. And voila, our radical in the right place there. So I was just redrawing that structure from the left. I'm going to draw it again, except to make a second resonance structure. I'm going to be moving the pi bonds and moving the unpaired electrons. So I'm drawing my second resonance structure here, just copying the stuff that's already down there so that we can use that within our mechanism here at this step 3. So go ahead and do that. And then last but not least, our third resonance structure, we're going to draw out here. So I'm just drawing in my resonance structure. Go ahead and get that all squared away and plug in my unpaired electrons. Get everything in the right places. So we should be good to go on this now. All right, so the propagation step, what's going to happen is that those radicals, you're looking around for what is available to react with. As they look around the reaction mixture, they're going to come in contact with Cl2. Cl2, as we mentioned previously, has a pretty weak bond connecting the two chlorine atoms, and that bond is particularly prone to homolytic breakage where the electrons evenly go to the two chlorine atoms. In other words, each of the two chlorine atoms become a free radical as a result of the reaction. So we're going to show that propagation step happening by taking the radical electron from our carbon. It's going to come over and team up with one of the two electrons from the chlorine-chlorine bond to make a new carbon-chlorine bond. The other electron from that bond is going to come over onto the chlorine, and we're going to do that same thing for each of these 3 resonance structures. So we're going to do the electron pushing arrows for each of those 3, like so, and we will go ahead and write out the products that will result from this. Okay, so we'll go ahead and get our monohalogenation product, mono meaning we've brought in one halogen atom into the molecule. So this is one of our possible constitutional isomer products. Also, we'll generate chlorine radical out of this step for each of these 3 scenarios. So we'll go ahead and make our next resonance structure into our next corresponding product here. So plug our chlorine atom in right there where the radical was. And then we'll go ahead and do that for the third situation here. Like so. Plug in our chlorine atom where the allylic radical was there in that resonance structure, and we are good to go there. The reason we call this a propagation step is because the chlorine radical that we've created here that I'm highlighting in yellow, that's a product of this step, can then jump directly back into the reaction at step 2, because step 2 uses chlorine radical as a reactant. Step 3 generates chlorine radical as a product. So steps 2 and 3 can cycle through and through and through, and that's why we only require one initiation step, and then this reaction can self-propagate just through steps 2 and 3 over and over and over again until all of the materials in the reaction flask are nearly exhausted, and then we go into the so-called termination step, becoming more favorable, which is where 2 radicals come together to create products that have no radical in any of the atoms, period. So the termination step is going to feature 2 radicals, reactants coming together to give a product that has no radical whatsoever. So therefore that's going to terminate the process because it yields no radicals to keep the reaction going. So that's our general mechanism for allylic halogenation, and highlighting this situation where you have a carbon that is allylic to 2 different alkene groups. If it's allylic to 2 different alkene groups, it's going to be most favorable for the halogenation reaction to take place there. So let's go onward now to another example of a reaction where we're asked to illustrate how the major organic monohalogenation products form. So in this case, we're starting with an alkane molecule, and the alkane molecule is treated with Cl2 with light and heat. Remember, the light and heat are what initiate the breakage of the bond between the two chlorine atoms. So just like in the last example, our first step here is going to be that initiation step. So we're going to initiate the reaction by breaking the bond between the two chlorine atoms. So we'll go ahead and do that. Cl2 with light and heat is what's providing the energy for this to take place. We break the bond homolytically because each of those two chlorine atoms are getting the same number of electrons out of this process of breaking the bond. One electron goes to the left, the other electron goes to the right. So this is going to give us two chlorine radicals. So we'll do 2Cl. And we have 3 sets of lone pair electrons, and then we also have that unpaired electron. So that's our initiation step. Step 2 is going to be a propagation step. So I'm just going to call this a prop step for propagation. And in this first propagation step, what's going to happen is that those chlorine radicals that you generated in step 1, the initiation step, are super eager to react because they don't really want to stay as a chlorine radical for very long. So they're going to swoop in and be looking for what bond they can most readily break here from our alkane molecule to enable us to yield the most stable intermediate that's possible. So they're going to be breaking one of the carbon-hydrogen bonds from our alkane, and the bond that we want to break here is always going to be the carbon-hydrogen bond that will lead to the most stable radical. And the most stable radical here, since we don't have any allylic radicals going on, is going to be the most substituted carbon radical. So the most substituted carbon radical that we can create here would be a tertiary carbon radical. And so we have to look for our tertiary carbons. And if we have more than one tertiary carbon, we'll react at both of them. But in this case, we have just one tertiary carbon. That's right here. The other carbons are all secondaries, primaries, or quaternary carbons. Carbons have 4 other bonds to carbon. So our tertiary carbon is going to be our location that we target here because that's what will yield the most stable radical. And we always want to yield the most stable radical out of this step. So we're going to target that carbon atom that I put the red star on. I'll go ahead and get rid of the red star for now so that we can draw out our mechanism in hopefully a nice clean way here. All right, and I am going to draw the carbon-hydrogen bond that exists here explicitly. It's important generally when showing mechanisms that you show the atoms that are participating in the reaction explicitly. So our hydrogen is participating, so we're going to show that. Radical chlorine electron comes over. It's going to team up with one of the 2 electrons from the carbon-hydrogen bond, so we showed that coming over, and those 2 teaming up with the single-headed arrows meeting up to give HCl. And then the carbon-hydrogen bond breaks, and the electron, one of the electrons from that bond comes onto the carbon there. So that's going to give us, as a result of this reaction step, both HCl as well as our carbon radical. So I'm going to go ahead and draw out my skeletal formula here. And I will plug my unpaired electron, my radical electron, on right here that we formed by breaking that carbon-hydrogen bond. And then what's going to happen next, going onward, we always ask ourselves, can there be resonance here? In this case, no, definitely there can't be resonance of our carbon radical because of the fact that there is no pi electrons and no lone pair electrons elsewhere in the molecule for us to share or move around the electron density. So we're stuck with this. So our propagation step here, step 3, what we're going to do is take that radical that we created there at step 2, and we are going to react that with what is most readily available in the reaction mixture. What's most abundant at the onset of the reaction, at least, is going to be the Cl2, is what's available and has a relatively weak bond, which we can break. So we're going to have our carbon radical come over, reacts with Cl2. So we go ahead and bring our unpaired electron radical over, team it up with one of the 2 electrons from the chlorine-chlorine bond. So we show those 2 coming together to make a carbon-chlorine bond. And then the other electron from that covalent bond to account for that is going to come over to the chlorine on the right. So we'll go ahead and show our product resulting from this. This will be our monohalogenation product. And that was what we were asked to demonstrate, how the monohalogenation product forms. So as soon as we get to the point where we've shown how that monohalogenation product forms, our work here will be done. We also create, as a result of this step, that chlorine radical. That's important and relevant in the same way that it was in the allylic halogenation reaction, in that this chlorine radical, that's a product of step 3, can then go back and participate in step 2 to carry on the reaction. So therefore, steps 2 and 3 can cycle through over and over and over again until we have exhausted the supply of radicals. Then we start to get into the termination step, where radicals will join up with other radicals to give products that do not have any radical in them. So our propagation steps here are yielding one carbon radical that can go on and propagate the process. So with that, we conclude our free radical halogenation problem-solving session. At this point, you should definitely be comfortable with writing out these free radical halogenation reaction mechanisms and predicting the major organic monohalogenation products of these reactions by thinking about, at step 2 of the mechanism, what is the most stable carbon radical intermediate that you can form there.